Let us continue the discussion on overview of experimental stress analysis. We have discussed in the last class the problems considered are beam under 4-point bending, cantilever beam, and the point to note here is when I do an analytical method, I am able to get the stress field, I am able to get the strain field, I am also able to get the displacement field. Now, the next problem is we move on to disc under diametral compression, and that is what is shown here. I have the disc and the center of the disc is taken as the origin. I have x and y coordinates and r is the radius of the disc. I have a diametral load P which is acting on it, and we will call this diameter as either capital D or small d. And for this problem you have closed form solution from theory of elasticity. You will not be able to approach and solve the problem from strength of materials, but you will be able to solve only from theory of elasticity, because plane sections do not remain plane before and after loading. You also had that problem in the case of a cantilever. When you have shear, the planes do not remain plane, they have a warping. Fortunately, there is no coupling between normal stress and shear stress, so you could live with flexure formula. That is why you call that as hinging analysis. The moment you come to circular disc, you have to depend on theory of elasticity. Fortunately, theory of elasticity provides this solution, and here again it is given in a convenient form sigma x sigma y tau x y, and you have this as minus 2 p by pi t, and I would request all of you to take down these equations. Though these equations are very long, it is very valuable information. When we develop photoelasticity, we could directly use these equations for our interpretation, and you have sigma x r minus y x squared divided by r1 power 4, and r1 is defined as r1 squared equal to x squared plus r minus y whole squared, and you have the second term is r plus y x squared divided by r2 power 4, and r2 squared is defined as x squared plus r plus y squared. We have already seen r denotes the radius, d represents the diameter, t is the thickness, and p is the compressive load applied. And you have the expressions are slightly different for sigma y and tau x y, and I would like you to have these equations written down. And obviously, the stresses what we see now, they are much complex than what we had seen in the case of a cantilever beam or the bending problem, 4-point bending problem. And naturally, you would not be able to calculate sigma 1 minus sigma 2 right away in the class and then plot the contours. So, we have to depend on computer graphics to do that job. When stress field is so complex, strain field is going to be much complex than this, and this is how the expression look like. And I have epsilon x, epsilon y, gamma x y, that is equal to minus 2 p by pi e t. And here again I would like you to make a decent sketch of you take down the notes of these expressions. I have this as alpha into x squared minus nu times alpha squared divided by x squared plus a squared whole squared, and alpha is defined as alpha equal to r minus y, beta equal to r plus y, and you have alpha and beta are also related to r1 squared and r2 squared as follows. You have r1 squared as x squared plus alpha squared, r2 squared as x squared plus beta squared, and you have this second term here is beta into x squared minus nu times beta squared divided by x squared plus beta squared whole squared minus 1 minus nu divided by d. So, this is the expression for epsilon x. You have a long expression for epsilon y, and you also have a very long expression for gamma x y, and though they are long, it is better that you have a copy of this in your notebooks, because this will help you because they are not readily available in the books that you have access to. Have you been able to make a copy of these equations? Okay. You have seen the stress field, strain field, both of them are longish, and definitely the displacement field is going to be much longer than what you have seen all along. So, it is better, please take your time to write it down, and you have this as u equal to minus 2 p by pi t e into 1 minus nu divided by 2. You have a tan inverse x by r minus y plus tan inverse x by r plus y. Then you have a minus of 1 plus nu times divided by 2 into r minus y x divided by r 1 squared plus r plus y x divided by r 2 squared minus 1 minus nu x by d. And on similar lines, you have a long expression for the v displacement. You have a term with natural logarithm x squared plus r plus y whole squared divided by x squared plus r minus y whole squared, and the expression goes like this. And obviously, it is very difficult to visualize what could be the nature of the displacement field by looking at this equation. If you have to plot, you have to go to a computer software, plug in these equations, have a plotting software to cull out the numbers, collect them, and then draw the contour. On the other hand, I take the model, I put it in the appropriate optics, I get stress information, I get displacement information. The moment you want to go for strain, right now we do not have a technique which will give a whole field strain information. You can get from strain gauges and plot them, or from displacement information you can do numerical differentiation and plot the strain. But right now you do not have a whole field experimental technique which would give you whole field strain data conveniently. Now, what we will look at is the circular disc under diametral compression is a benchmark problem in photoelasticity. So, we will see the photoelastic contours, and we will also see another set of an experimental arrangement where you get contours of sigma 1 plus sigma 2. In photoelasticity you get contours of sigma 1 minus sigma 2, and I said one experimental technique will not give all the information. Suppose I want to find out information, of individual stress components. One approach could be do a holographic experiment, get simulated, I get isopatchics recorded, in this case it is simulated, but get the isopatchics recorded. So, when I have photoelastic contours as well as holographic contours, I can process these two and find out individual magnitudes of sigma 1 and sigma 2 on the entire field. And what you have to note it down is between photoelasticity and holography, I have showed colored contours for photoelasticity, because you use white light and get information in color which is unique to photoelasticity. Although it also gives monochromatic information, many techniques depend on monochromatic light source and you get black and white information which is processed. Holography, you do it only on a single wavelength and the contours are very similar, and I would like you to have a reasonable sketch of this, any one of it, which gives you an indication how the fringes look like. And here you have this as a shape of 8, this as a shape of 8, this you have to note it down, this we will use it in our experimental interpretation later, and you can also see as a function of load applied how the fringes develop. So, what happens is fringes develop here and move outwards, that you could see from these simulation. This also gives you an indication of doing an experiment right at the laboratory. Same thing you can do for photoelasticity, fringes develop and move outward, and this also gives you an indication how you can go about in labeling fringes, which is a very complicated exercise, we will see later. So, In this example, we have also shown result from holography, and if you want to go for displacement information, what is the technique that you will use? We have been seeing Moire. So, I would see the Moire contours, what I get for u displacement as well as v displacement. How do I decide that? I have the grating direction with which it is recorded, and you get these contours beautifully, and we saw this very difficult expressions, and obviously when you do it, it will be complicated like this. And I can also change the load 1, 2 and gradually increase the load. I see more and more fringes appear, and probably this sketch you can make because you do not have many fringes, but it gives you the geometric shape of the fringes reasonably well, because at a later point when you have occasion to see the experimental result, you could easily say I have seen these patterns earlier, and they would be for a disk, it is only u displacement. Suppose somebody gives you a photograph without the grating direction on an unknown situation, if they want you to interpret, you will not be able to give an answer immediately, unless you know how the experiment is conducted, how the values are recorded. You will not be in a position to interpret the fringe patterns. Interpretation requires additional information. Labeling of fringes is not a simple task, and for that we will have to know what are the various techniques available to label the fringes. And some of the later examples I have not shown the fringe ordering deliberately, so that you can do this as an exercise and label the fringes after we have learnt the course. So, when I increase the load, the more and more fringes appear, and that is what I see in the case of a disk under diametral compression, and this gives you u displacement. And now similarly we will also see the v displacement, and this is what you have here. The grating direction is like this, and as I increase the load, I go from this, gradually go from this. You find this is the load application points, and all the fringes come from this, and what you also find, you have a very broad fringe, and as you increase the load, you have the fringes move and occupy different positions. So, it is possible for you to label them appropriately. If you have this knowledge, what you find is this fringe has moved at a very high load. So, if you have the number attached, the number also will move along with it, and here again you can make a reasonable sketch for a intermediate load to know the nature of the displacement field. So, that gives you certain level of familiarity, and you feel closer to an experimental technique, and you also get a knowledge how to appreciate visual information. And for this example, I also have another set of contours what you can get from photoelasticity. Photoelasticity can also give you principal stress direction, and that is what you see here, and we will see this closely. So, what I find here is I have experimental isoclinics, and what you find here is the whole image looks blurred, a black contour moves over it, that is what you see, a black set of contours move over colored bands. Can you identify the colored band, because you had seen this earlier? Can you identify the color band? You can identify the color band. What the color bands show?
Isoclinics.
They are contours of sigma 1 minus sigma 2. So, what you find here is, in this optical arrangement I get two information. One information is sigma 1 minus sigma 2, another information is the orientation of the principal stress plane. And what you find, if you have two information superimposed, the clarity is lost. So, you would always like to have independent information, then processing, data collection, everything becomes much simpler. And what you see in this example, I have one set of contours that move, and this you may not be able to understand at this stage. What it indicates is the direction of polarizer, analyzer. These are two optical elements, they are kept at mutually perpendicular degrees. For these angles, these contours move. So, what you will have to do is, from a data collection point of view, I have to set it at fixed angles and try to make a reasonable sketch of what these contours are, and that is what is shown here. So, what you have here is, I have the set of contours which is a binary plot in steps of 10 degrees, this you make a sketch of it. So, I have to process this information and extract this in this form. I do not have an optical arrangement which would give me this set of contours directly. So, I have a 0 degree isoclinic, 10 degree isoclinic, 20 degree isoclinic, 30 degree isoclinic, and so on. And we call this as isoclinics. Iso means constant, clinic means inclination, isoclinic means contours of constant inclination. Constant inclination of what? Constant inclination of principal stress direction. So, from a photoelastic experiment, it is possible for me to get sigma 1 minus sigma 2 contours, and you can also get, by an appropriate optical arrangement, contours of principal stress directions. And what I find is, here I have sigma 1 minus sigma 2 contours superimposed over isoclinic contour, and I do not see all isoclinic in one shot. I have to scan the image and pick out this information, get this as a separate image of isoclinics. So, without getting into the experimental details, I have tried to project what is in store for you. In some experimental technique, you get the information separately. In the case of Moire, I can get u displacement, I can get v displacement separately, and getting them separately is better. Though I have to do one more experiment, getting them separately in an optical arrangement is far better from processing point of view than getting the image of sigma 1 minus sigma 2 superimposed on the isoclinic pattern. Thank you.